And our final speaker is Eric Brown.
Good morning. It's really a privilege to be able to talk to this audience of very well-known engineers and the conference committee here. After yesterday's very interesting session, however, I find myself with a bit of an identity crisis. In the education session, I believe Professor Chris Wise gave very crisp definitions of a scientist and engineer, a scientist being somebody who observes the natural world and tries to make sense of it in here, while an engineer tries to create things in here and produce them out in the world. But I give my profession as a computer scientist. And as I thought about that, I thought, well, there aren't computers out in the wild that I'm trying to understand as a scientist. So am I a scientist or an engineer? And I thought about it a little bit more, and actually I work on the software side of things, and as we call ourselves software engineers, we actually often find ourselves doing battle with the hardware. And the hardware is, in fact, somewhat of a foreign object that we're trying to understand. So there is quite a bit of science there. And this notion was further confirmed just moments ago when I was talking with Neil, who was saying that he suspects that this whole von Neumann architecture is actually all wrong. And that explains why software and hardware struggle to work together at times. So, this notion of what a scientist is actually is a little more relevant to my topic today, which is the meaning of the word scientist depends on the context in which you're using it. And this phenomena is actually common to natural human language in general. And what I'm going to talk about today is technology that's all about trying to understand human language and deal with these challenges of the nuances of language, the ambiguities of language, and the fact that its definition is so contextual and can change over time, in fact. So I want to touch on really 5 quick topics here. First, this notion of big data, and it's a topic that was hinted at yesterday, but hasn't really been discussed yet, and it's really this notion of, not in the physical world, but in this world of data, how do we leverage all of this data and actually evolve it from raw data to information to then actually knowledge that we can act on. And the technology that we believe will evolve to help us do that is something we're calling cognitive systems. And so I want to talk about this Waston system and introduce that to you as an example of a cognitive system. Talk briefly about how we've actually leveraged Waston to demonstrate it as an example of STEM technologies. And it actually, as we've demonstrated it on a television show, is one example of sort of combining this notion of entertainment with technology to make it a little more publicly interesting and palpable. I'll talk a little bit about the keys of building Waston, and then finally some applications of Waston to healthcare. So let me start with this notion of big data. And really the challenge here is recognizing that data is just growing at a tremendous rate. And in fact, 90% of the world's data was created in the last 2 years. And so in business, this is a huge problem for people to leverage that data and make sense of it and apply it to their business. And in particular, the fact that 80% of this data is unstructured. And so, for example, text, a form that computers typically struggle to deal with, it is a serious problem that we're trying to address. And it's just a growing problem, especially with so many devices here, 1 trillion devices connected that generates an exabyte of data in a year. And to give you a specific example from the healthcare domain, you can see that this is a big problem in healthcare as well. The amount of medical information is doubling every 5 years, yet physicians have very little time to actually keep up with all this data. Some surveys show that more than 80% of physicians spend less than 5 hours a week. Actually, I think that chart should say 5 hours a week, keeping up with the latest medical literature. Yet, we all know that it's critical for physicians to keep up with that literature and be able to apply the latest research results and best practices. On top of that, you see some challenges in healthcare in general. A lot of these issues were discussed yesterday. In the U.S., for instance, we waste about 30% of our healthcare dollar due to problems in healthcare. And so this is a huge opportunity to make improvements and, in particular, leverage big data or unstructured information to solve those problems. This is a chart we like to use that we call the hockey stick chart at IBM, which gives you a sense of the growth in data. That the left-hand axis is giving you the volume, the right-hand y-axis just applies to that red line, which says what percentage of this data is uncertain. And you can see where we are today with nearly 3 exabytes of data. That's 10 to the 18th. But the growth trend is really quite shocking and suggests that this problem of big data is just growing and is really something we need to tackle. And the way that we're going to tackle that is by leveraging what we call cognitive systems. So now, we've taken a fairly high-level and coarse classification of computing and decided to separate the initial era of tabulation from the second era of programmable computers to now what we believe is the next era of computing that we're calling cognitive computing systems. And this is not to say that cognitive computing will replace programmable computers, but will start to enhance and produce solutions that are required to address problems in this big data and unstructured data era. And there are really 3 key elements to cognitive computing that I like to think about. One is, initially at least, it's all about expanding human cognition, developing technologies to help humans apply the power of their brains by giving them better, more efficient access to all of this data so they can factor that into their very sophisticated reasoning process. And we see that when we talk about applying this technology in the medical domain and creating decision support tools that can give physicians access to this huge volumes of medical information. The second aspect is more natural interactions between humans and computers. So in the programmable era, humans have been forced to adapt the way they work to the way the computer works. In this cognitive era, we imagine the computers really adapting to the way humans work and interacting much more naturally. And the third key element of the cognitive era is this notion of learning in a whole variety of ways to scale these systems out to address these big data issues. We can't simply reprogram them every time we come to a new domain. We have to come up with learning techniques that allow these systems to adapt automatically as they're used by humans. So let me give you a quick example of some of the challenges of dealing with natural language. And so first, computers are very good at dealing with structured information. So if I want to know who ran GE or what company did Jack Welch run, if I have a database of structured information with a table that says people and the organizations that they ran, it's very easy for me to extract, or for the computer to pull out Jack Welch as the runner of GE. However, if I wanted to answer that same question from unstructured information, and I had this sentence, if leadership is an art, then surely Jack Welch has proved himself a master painter during his tenure at GE. Now, how do I find the answer to the question, what did Jack Welch run, or who ran GE? From this sentence, we might infer, well, at least Jack Welch was a really good painter at GE. But if you read the language, you know that this is really a way of describing Jack Welch as the person who ran GE. And in natural human language, there are just so many examples of the ambiguity and challenge of dealing with natural language. You know, noses that run while feet that smell, how can houses burn up as it burns down, etc. So this is an interesting challenge of dealing with natural language. And we've tackled this problem by starting with question-answering technology. And this has actually been an active area of research for decades. You can go back to 1970 and find a paper in the Communications of the ACM that's a survey of the state-of-the-art in question-answering. So now this is 43 years ago, where question-answering technology was being summarized. Yet, as of the early 2000s, the technology really had not matured to a point where it could be applied in a commercially viable way. So it was at this stage when, at IBM, we decided to really drill down into this problem and elevate it to what we internally called a grand challenge problem and really tackle it. And this was the emergence of the Waston system as a problem to try and solve and address challenges of question answering. The way that we wanted to demonstrate this was in a very public way And somebody hatched this notion of building a computer system that could compete on Jeopardy. So for those of you not familiar with Jeopardy, it's an American quiz show. It's actually quite popular. It's been around for, I think, since the 1950s. The current format has been around for about 25 years, where you basically have 3 human players answering questions. There's a clue board with 6 categories and 5 clues in each category with different clue dollar values. But the clues are not initially revealed. So a human will pick one of those clues. The text of the clue is revealed. The host reads the clue. The 3 players attempt to come up with their answer. And then when the host is finished reading the clue, the first person to ring in gets to answer that clue. This is basically how Jeopardy works. We wanted to build a computer system that could compete on that quiz show at the same level as a human champion. And here you see some of the elements of Jeopardy that make it fascinating. It has a broad open domain. It deals with complex language. It requires high precision, accurate confidence, and high speed. And so these were all of the issues that we needed to address in this technology to solve this quiz show problem, and yet they transfer directly to a number of business problems. Now, I said I would talk about how we applied this to the problems of STEM and reaching out to students. I happened to be visiting a middle school and talking about Waston and presenting it to some students, and was using this real Jeopardy clue as an example. And this is from the category Lincoln Blogs, and it's about the 16th American president, Abraham Lincoln, who was president from 1861 to 1864. And the clue is Treasury Secretary Chase just submitted this to me for the 3rd time. Guess what, pal? This time I'm accepting it. Anyone want to hazard a guess as to what it is? His resignation. That is, in fact, the correct answer. And the challenge of this question is, if you're not familiar with Abraham Lincoln or Civil War era U.S. history, you might not know the answer, so you have to look at the contextual clues. What are things that are submitted? What are things that are accepted? And we're talking about politics, so being cynical, we probably will assume that it's a resignation that is being submitted. I posed this question to some 6th graders when talking about Waston, not really expecting them to know. One girl raised her hand, and very bravely, and she responded, "What is a friend request?" And so I found this answer fascinating on a number of levels. Now, I'm sure that if Lincoln had had Facebook back in 1860, he would have been friends with Chase. But what's more interesting is how the definition of, or the meaning of submitted and requested, again, very contextual. So for the 6th grade student, that goes to a friend request. And again, speaks to the challenges of dealing with natural language. So this Waston technology, which I'm not going to have time to go into in much detail, is all about applying a whole series of different areas of research, from natural language processing to machine learning to information retrieval to knowledge representation and reasoning, and ultimately building an architecture, and now I'm talking about software architectures, that allow us to combine and integrate all of these analytics, and in fact over 100 different analytics, and then using machine learning to weigh and combine all of the results to come up with answers. So here's a brief history of the project and some general areas that we consider interesting. I just want to highlight one topic in particular, which is the application of this technology to the healthcare space. Our research team is collaborating with the Cleveland Clinic to address, again, this challenge of leveraging all of this medical knowledge to assist physicians. And in particular, we're working with their Lerner College of Medicine, which uses what they call problem-based learning, an approach to education that was discussed quite a bit yesterday. Rather than learn from textbooks, they take their medical students and break them up into small groups and give them rich problems to then drill down into, diagnose, and essentially work through a case study. We're looking at ways to apply this Waston technology to both support that research and case study process and also allow students to interact with the system in what we call a collaborative learning system to actually help Waston become better and more intelligent and work us towards this notion of a cognitive computing system. So let me just finish by saying what I'm really talking about today is knowledge as essentially a natural resource, but in order to leverage that natural resource, we have to have technologies like cognitive computing systems that elevate it from data to information to knowledge. And thank you very much.